Hi, it's time for another Hero Junior video. If you watched the previous video, I worked on the steering and drive systems as well as the power management system. In this video, I'm going to concentrate primarily on getting the head so that it can turn. So the original Hero Junior, the head was fixed. It was mounted directly under the body. It could not turn. This is in contrast to the Hero 1 robot, which did have a turning head as well as an arm. But the Hero Junior's was fixed. So I have spent a lot of time working on coming up with a mechanism so that I could make the head turn. Over the last few weeks I've made a few other changes, like I added handles. It is convenient to have handles on the side of it. I 3D printed those. I'm not quite happy with the color of the handles. I might look for some other filament that's a different color. Another thing that I did was to replace the pin and grommet system that was in here with some magnets. So now, rather than having to struggle, these pull off easily. You should be able to see the magnets mounted on this side. I got magnets that had holes in them for screws. And then not necessarily visible, there are magnets on the back sides of the aluminum here that these magnets will be attracted to. So you got to kind of position it just right, and when you do it, just snaps in place, and it is, you know, it's on there reasonably solid. Okay, it's time to do a little bit of mechanical engineering. One of the things I wanted to do was to make the robot's head so it could spin under robot control, so it could look around and it could do its sensor measurements without having to turn the whole body. That's one of the things I disliked about my original Hero Junior back in the 80s and 90s, is that to try to pick a direction to go, it would have to turn the whole robot around. And, you know, potentially it's bumping into things while it's doing that, even though it can turn kind of tight. And it's also kind of slow to turn the whole robot around and try to do a sensor sweep. So I came up with an idea where I would take the head, rather than fixed mounted. It used to mount to these 4 holes on the top there with some studs that went through and hooked the head down. I would mount it on a bearing system. So what I have here is a Lazy Susan bearing. I got this off of Amazon. It does have balls in it. It is a ball bearing. And people use these to build like food racks and spice racks, and you could put something on it and set your food stuff on it and turn it around. It's kind of a popular kitchen thing, I think. But it supports hundreds of pounds, so it certainly ought to support the little robot head on there. And it spins relatively smoothly, it's durable, it's made out of metal, it's got easy mount points. So I came up with that, and then I came up with this black, you can kind of see it, this black 3D printed bracket beneath that has a hole pattern that mounts to the Lazy Susan bracket and then comes up with some holes that mount into the robot frames. Now we've got a nice place where we can turn the head. Now to spin the head, down in here, and I don't know how easy it is to see, let me see if I can flip things a little sideways, we have a gear motor. That is a 12 volt 27-to-1 gear reduction motor that I got from Stepper Online, I think it was. So it was a little bit hard to find a 12 volt motor. I'm still sticking with this design where rather than using the Pololu stepper controllers, I'm using an H-bridge and I'm driving it at high voltage rather than low voltage. Due to the back EMF, most modern stepper motors are low voltage, high amperage. I kind of didn't get a chance to kind of tweak my controller design, and I stuck with the original design. Now, in order to control the head motor, I had to rebuild my motor controller. So you recall in the previous video I showed off the motor controller. It controlled the drive motor as well as the drive stepper via some of these TB6621 H-bridges. I think it had an Atmega 328 28-pin microcontroller in it. I decided to add one more H-bridge. You can see another TB6621 there, and switch to a bigger Atmega controller. I think this is an Atmega 324. So I just extended the design to one additional motor controller and a bigger microcontroller to run it. So what goes on top of this is another 3D printed bracket. It's got holes in the middle that'll secure to the hub, and it's got holes around the side that'll secure to the Lazy Susan bracket. Kind of plops on like that, and then the robot will be able to turn this whole black thing round and round like that. Now, I wanted to come up with a solution for attaching the head that didn't involve me having to reach up inside of here and screw something down, because it's really kind of hard to get around in there. So I've come up with a solution with magnets. So you'll see these kind of big holes going around here. Those are ones where I can push in 10mm magnets. Then I've built myself a corresponding bracket for the robot head. And it's got 10mm magnets, and it'll stick on there just great. And that is how we will attach the robot head. There's one last thing to figure out, and that, well, actually two last things to figure out, and that is power and communication. So the robot head obviously has electronics in it. You know, it's going to have sensors, a camera, a keypad, LEDs, all that good stuff. We need to get power to it. And we also need for its sensors to be able to talk to the board that's running the drive system down here. So taking the communication first, that's the easier thing. Raspberry Pi has Wi-Fi built in. I am just going to try to set up a wireless link between the head and the body. That's kind of a split brain approach. You know, there's going to be some smarts in the body, some smarts in the head, and it's going to have to coordinate. It's going to have to rely on low latency between the two. I'm going to kind of keep my fingers crossed that we can keep the latency down low enough to work. But that solves a lot of engineering problems with that communication. I thought about using a slip ring, which is kind of a brush and contact thing, but slip rings, they can be kind of dicey for I2C is what I've read. So I really figured let's just try to do wireless communication. That leaves us to get power to the head. And what I am thinking is I've taken out my ohm meter and I've measured this. I get relatively low ohms, like 0.1 ohms or so, in this Lazy Susan bracket between the bottom stationary part and the top turning part. So that would give me, I think that would give me a pretty good ground. And then similarly, through the motor shaft, the metal shaft that goes up through this motor to the motor body, I'm also getting really low, like 0.1 ohms through that motor shaft. So this motor, it's a lot of metal in here. It's got metal bearings between the shaft and the body. So I'm thinking I will run my battery voltage up through the motor shaft. So ground can come up through this outer bearing. 14.4 to 16.8, you know, whatever my battery voltage is, can come up through the motor shaft. We'll regulate it down inside the head. Even if we lose a volt or two to resistance, we still got plenty to regulate it down. We only need to pull about an amp to run all this electronics that are going in the head. So I think that's going to be my solution. And then furthermore, rather than having a plug in here, I will just take and I will run the juice through a couple of these magnets. So in order to make this work, I had to figure out how to attach leads to my magnets so I can pass power through them. So the first thing I did was to try soldering to one of the magnets. So here is a 10mm magnet with wire soldered to it. I actually heated up my soldering iron extra hot to like 390 Celsius because I figured this kind of a big piece of metal, maybe I want to get it plenty hot in order to get it to the temperature where the solder will melt to it. And it worked, and it is indeed still magnetic. But then I read online that you should absolutely not do that. You will heat the magnet to beyond its Curie temperature by soldering to it, and you will ruin the magnet. Well, clearly the magnet is not ruined, but it is maybe diminished from its normal magnetism. So I decided, let's not keep doing that. Let's come up with a different technique. So I bought some MG Chemicals silver epoxy, conductive epoxy. Very nasty stuff with lots of warnings on it. Kind of expensive, like about 40 bucks for these two tubes. And we can do that to epoxy some wires onto these magnets without soldering them. So you can see that is, oops, they're sticking to one another. There's a lot more magnetism left in this magnet that I used the epoxy on than there was the one that I soldered to. So I prepared Plenty of magnets, some of them North Pole up, some of them South Pole up. With this conductive epoxy, I epoxied the wire on it. See, my meter zeroes out at, what, about 0.2 ohms. Let's go from this wire to that magnet, and 0.1, 0.2, so it's negligible is what we're reading through that conductive epoxy. So the conductive epoxy seems like it's going to work out really well. I'm going to take these magnets, I'm going to mount them in the plastic parts for the robot head, and this will be how we transmit the power from the body to the head. Okay, here you can see the base of the robot with the head removed. I just wanted to show the wiring before we put the head on. And you can see I've got a total of 2 magnets here that are hooked up to ground and hooked to the Lazy Susan bearing. And 2 magnets here that are hooked to battery voltage and go through the motor shaft. Now the motor, even though it is gear reduction, you can still put enough torque on it to turn it, so you can kind of see how it turns. And you can see that in here I have placed a Hall effect sensor, and then right here, I don't know if you can quite see it, but there's actually a small magnet stuck there in this piece so that the robot is able to tell when the head is home to the front like that. So I'm going to turn the power on, and then you will see the robot do its homing, which will be to seek until it hits the Hall sensor, then to seek until it hits the opposite side of the Hall sensor, so when it tells it's moved off, and then seek back. That kind of helps it to eliminate the dead spot in the middle where the Hall sensor is always sensing and figure out the exact 2 edges of the Hall sensor. So let's turn on the power. So it's seeking all the way around. Hit the Hall sensor, passed it, seeked the other side, and then came back. So now it is centered and it knows where the center position is. The noise you're hearing now is it's still doing its centering of the steering wheel. So then we can attach the head, and you can see the head, the green light has come on because the head does get its power through those magnets. And just like I did for the body, I designed a breakout board for the head as well. So you're looking at the head from the bottom up, so there you go, looking inside the head, and you can see the breakout board that I designed here. Again, just like the body, it's an Atmega AT324 CPU. I've got a little voltage regulator section over here. And then for the most part, this is just a huge breakout of various things. There's actually a Raspberry Pi hidden underneath via that header. And then we've got a big pin out here going to the keypad. Power coming in from the magnets is coming in over here on these wires going into the voltage regulator. Breakouts for the sensors I plan on adding, stuff like that. I'm not really going to go into any detail on this head breakout in this video because I want to wait until the next video when I actually have acquired some of the sensors, and then we will know that I actually put the right pinouts on this thing for those sensors. Okay, so I have my handy remote control here with Raspberry Pi built in, and we can use it to operate the robot's head as well as its drive system. So I've taken the 2 trigger buttons and I've hooked them to left and right on the head, so we can go one way or we can go the other direction, and then this button here will cause it to home back to the center position. So the nice thing about this is it can actually go 360 degrees all the way around. If I push home, it'll automatically home by whatever the shortest direction to get back to the home position is. So we can kind of sweep it around like this. Let me home it back up. And then just like before, the drive system continues to work. Forward and back. Oops, hit my foot. And we can actually run them both simultaneously. So, we can certainly drive and move the head. We can steer. So this is really working pretty much just like I had hoped. Now the rotational torque on the motor is actually pretty good. You know, I can put my hand here and add a little bit of drag and we're not stalling it, which is great. I can actually add quite a bit of drag, but if it actually did hit something, if there was actual interference, it will actually stall like that. And that's actually a good safety feature because, you know, you can't get your fingers pinched in it or something. It just doesn't really have the torque to cause too much trouble. Of course, if you do stall it, then it'll get confused about where home position is because it lost steps. So like right now it thinks home is over there. So I'll have to write in a feature to recalibrate it if it does get stalled. Now another thing I've acquired for next time is some TF Mini sensors. So the TF Mini, let's open this one up and look at it. It is actually they call it a LiDAR sensor, but it actually does not have a laser, so it is not technically LiDAR, but it is a time of flight sensor that sends out pulses of infrared light and then measures the time for those pulses to be reflected back. And supposedly this is a decent quality one. Not as good as a real LiDAR that would use a laser, but still decent quality. Now with the robot, I'm going to include a sonar sensor since that is iconic. Every Hero robot had a sonar sensor, but I'm also going to include 2 of these to get more precise sensor measurements. So I think one of them I will point straight out so it can do room mapping, but then I want to take a second one and point it down at like a 45-degree angle. And that, I'm thinking, would allow the robot to see obstacles in front of it. Something like a coffee table, something that might fly under the horizontally facing one, but see obstacles as well as be able to detect if it's about to go off the stairs and fall downstairs. Now I also got some goodies from Robert at Robot Workshop. So when Heathkit went out of business, Robert bought up their old inventory of parts as well as the copyrights on a bunch of their manuals and other stuff. So if you are missing documentation or you need parts, you can go to Robert's website and he might have some of the stuff you want. And one of the things I wanted was an SC01 speech chip like the original Hero Junior had in it. This is actually a speech board out of the Hero 1. But right there, it does have the SC01 chip. Robert sold me this. These things are pretty expensive because this chip is super rare. I'm going to pull this chip out of here. I'm going to design my own board to interface this with a Raspberry Pi and put it in the Hero Junior project. And then we will be able to have the Hero Junior speak with the original Votrax speech synthesizer. I thought about trying to emulate it in software, but there's just no substitute for the original hardware. So we'll be going over that hopefully next time. Another thing I got from Robert is the Hero Junior main ROM listing. Now, again, this is copyrighted material. The copyrights on this are still valid, so I can't like flip through and start showing code in it, but this includes the ROM listing for the Hero Junior. It's all in assembly. It's like reasonably well commented. It's not great, but it's good enough that a person ought to be able to look at it and kind of figure out what the original behavior of the robot is. Even if I don't use the code, the comments in there will tell how it functioned and how it did the various games and the various modes and such. Because one of the things I want to do is to be able to reproduce the original behavior of the robot. Now this is all in assembly. And one thing that's interesting is I came across this webpage by Donnie Savage on his website where he says that the source code for the Hero Junior is written in PL1 with some assembly drivers. Now, unfortunately, the link on Donnie's webpage, it doesn't work. I click through, it goes to a 500 error response from his server, and I haven't been able to get a hold of him to find out what's going on with that. But that's interesting because when I talked to Robert, Robert said, no, it's definitely all in assembly. Certainly this whole book is in assembly. Unless something is going on, like there was originally some PL1 source code, and then what got distributed here is the output of the compiled PL1 into assembly, maybe, I don't know. Or the reference on Donnie Savage's page is wrong, or it was cut and pasted from one of the other robots or something. I'm not sure, but it's an interesting mystery as to whether or not the PL1 source code exists, and does anyone have it. I might try contacting Donnie Savage again just to get to the bottom of the mystery. But it's really curious. So if anyone does know whether there was PL1 source code for the Hero Junior, please do send me a comment and let me know the answer. If you actually have that, that would be even better yet. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.